Hello, Houston. We have now finished just over 2/3 of the course, and most of you have taken an exam based on the material up to and through the last tape. This is probably perhaps one tape too late to remind you that you should not now be viewing this tape a week before the final exam. It would be better, if you remember from what we talked about on day one, to spread out your viewing, engaged in distributed practice, so that you're viewing 1 or 2 tapes a week. 8 hours of me at one shot is very, very much to ask of anybody. So we would generally recommend that you spread the viewing out quite a bit more. Now what we're going to do is jump over into a discussion of problem solving, and what we show occasionally when we're engaged in problem solving, and that is creativity. Basically, it's required problem solving anytime we have goal-directed behavior that has been hindered in some way, that is something is artificially interacting with us and frustrating our attempts to solve particular problems. And that puts us into the issue then of problem solving. We're going to define problem solving simply as overcoming obstacles which obstruct or frustrate the achievement of a solution. Hinder, in other words, the achievement of a solution. We're taught problem solving in many different college classes. Some are just factually oriented, others are hands-on, get yourself involved in what we're talking about here. Labs in the physical sciences are very good examples, and in some of the social science classes are good examples of hands-on. Here's a problem, how do you go about solving it? So we're taught in a lot of different ways to deal with problems, and professionally that's what many of us are doing. When we're operating, whether it's as an MD or as a lawyer or anything else. We have a problem, somebody is brought to us, and we apply our professional skills in trying to figure out how to do it. So the nature of the problem varies quite widely, certainly as widely as the many different disciplines in which we might major. But what all the sciences share in common essentially is a constructive attitude toward problem solving. That is, they are an organized set of principles, organized at different levels, whether you're talking about physics versus psychology. But regardless of the science, the labs are basically oriented toward teaching skills with which you and I can overcome the challenges of the discipline, create a new substance, identify a mystery substance, or anything like that. So we're going to find as we look at this today that there are a lot of different types of problems that we may encounter in our study of problem solving here. The underlying issue here is, can we learn from one problem solving situation skills that will help us in later encountered problem solving situations? That is, can that knowledge be transferred to other variously similar situations? And so when we look at problem solving, we're not only looking at solving the individual problem, we're also looking at the issues of what do we learn from that we can carry over to other examples of such problems. So in terms of the various kinds of problems that are encountered, the underlying issue here is, can we learn from one problem and carry it over to another? What that leads us immediately into is the need to be able to classify what we're talking about. That is, the problem of debated similarity of problems psychologists have studied leads to a very significant need to classify the different types of problems that we're actually talking about. Greeno, way back in 1978, suggested that there are 3 basic classes of problems that kind of capture the essence of what we're talking about in psychology when we talk about problem solving. The first of these that he talked about is what are called arrangement problems. Arrangement problems are basically, in fact, we're going to go ahead and define it for you, essentially as an unsolved condition that requires elements to be sorted or viewed in a new or unique manner to satisfy a specified criterion. So in essence, in that situation, arrangement problems are essentially where the goal is to take the presented elements, whatever you're presented with essentially, and arrange them in a new way. That is, try to create some new kind of example that responds to whatever the solution demand is for the particular problems. Many different orders of letters in words, for instance, may be possible, but only one really satisfies the demands of the problem. For instance, if I give you a series of random words, random letters, I should say, and ask you to find a word, In some cases, there may be 2, maybe even 3 solutions, but not usually. There is a single order of the letters which actually defines the kind of issue that is being raised here. So in essence, what we're going to look at, first of all, and in terms of arrangement problems, are what are called anagram problems. Anagram problems essentially are puzzles that require rearranging a limited number of letters that have been supplied to you to form a word. And we've already written down what I'm going to tease you with here on tape in the book that you're writing in. But what kind of thing, whoops, I hadn't given you the definition on the screen there yet. Sorry about that. A puzzle that requires rearranging a limited number of supplied letters to form a word. That is an anagram. So if we give you something like sassiness, what word can you make out of that? What word can be made out of the rearranged letters of sassiness? Yes, we actually talked about that once before. Assassin. How about no south? No south. You're going to be embarrassed at how easy that one is when you figure it out. No south. Yes, but you have to be on mic to get credit for it. Houston. Houston is no south. Therein lies one of the problems with problem solving, because if you notice, in that particular sequence, the T's, the puzzle, included TH, which is a high probability letter sequence in English. And a number of you were probably trying to move TH somewhere else in the word to make or the combination to make a word out of it. But in that case, it doesn't serve well, because Houston, of course, does not have the TH in either order. They're not even connected with each other in the solution. So in some cases, the strategies that we may want to use sometimes work, other times may not work in a given situation. How about Gaminar? Gaminar. I'll give you that one. Anagram. Anagram. How about Guinness? That's not a World Book of Records. It's an anagram. Guinness.
Insight?
Yes, it's what you need to solve anagrams. Insight. How about Sachuska?
Cash out?
Yeah. And then how about Einsteruvi? I love this one. Einsteruvi. Get a little tougher when they get longer, don't they?
University?
Yes. University. Einsteruvi. So you're going to the Einsteruvi of No South. Sorry, the Einsteruvi of No South. And so in essence, there are a series of arrangement skills that are required in order to solve anagram problems, because you have to be able to keep in mind, first of all, what you've already tried, and thus don't waste time trying it again. You've also got to keep in mind, which letters have I used, which have I not used as you're going through it. And it begins to get a little difficult when you get to something like university, because that is more letters than you have ability to store in short-term memory. But in essence, there are a number of skills that do tend to show up in this situation that can be very helpful in solving anagram problems. Excuse me. One of them is fluency in generating possibilities. The best kind of a solution there is one where you can generate even partial solutions and then discard those that are unlikely to be fruitful as you look how to fill in the letters. So as I was suggesting with No South becoming Houston, that TH is a very tight combination of letters because it occurs very frequently in English. That was a strategy which in that case would not particularly help. But for anagrams, knowledge of letter orders is highly desirable. We don't tend to think if any of those had a J and a Z next to each other, we don't tend to envision a word word that puts those two letters next to each other, because that just essentially never happens in English. So your knowledge of the language is very helpful in generating possibilities with which to serve anagrams. A second element that is also very helpful is being able to retrieve solution patterns. If there are patterns of letters, even that happen to occur over and over. That's another way, essentially, to retrieve possible words from long-term storage should aid in generating solutions. That is, if you can pull words that are out of memory just wholesale, solve it in a gestalt, that's one strategy to follow in problem solving. We're going to look at some of those strategies later in logic, but that would be essentially kind of fishing randomly through long-term memory and see if you can come up with words just wholesale rather than trying to spell it out letter by letter by letter. So ability to retrieve patterns can be another skill that will contribute positively to anagram solution skill. Another one, a third factor, is knowledge of the principles that are constraining the search. Okay, knowledge of letter frequency helps. Okay, so you tend to try to position the most popular letters first. And as I pointed out, the Houston as the solution to no south, the TH rule in that particular case probably frustrated solution. So hopefully you didn't invest too much time in that. Although I would suggest that the reaction time was perhaps slowest for that one and Einsteruvi as the two. The second one probably because it was so much longer. But these are problems where insight can be very valuable. We're going to discuss that more a little bit later. But in essence, the solution then of anagram problems is based on at least three different skills that we hope will contribute. Fluency in generating possibilities is one. A second is retrieval of patterns that may fit a solution. We know that in syllables, particular word orders or letter orders tend to occur more frequently than others. And then finally, the knowledge of the principles that may be restraining the search that you've got. Among other things, for instance, no word that includes anything beyond the letters that you've been given will be allowed as a solution. Now let's look at another kind of problem which looks at it in a very different way, problem solving, and that is to look at essentially organization problems. This is another form of arrangement problems put in a slightly different form. And now what you're going to have to do is to engage in what some people would refer to essentially as thinking. You're going to become much more reminiscent of the thinker as you get into the next series of problems. You'd be amazed how far I had to look on the internet to find a picture that I could use of Rodin's The Thinker. But in essence, what we're dealing with here is the following kind of thing. The first one that we're going to talk about is what's called the candle problem. And here's where I'm going to ask the guys in the booth to focus in very tightly on what I've got sitting on my desk here. I was going to throw in a piece of string as a distractor, but in essence what we're going to do is to show you essentially this particular problem set. We've got a box, which I'll show you is filled with thumbtacks, okay? The kind of thing that you see on the desk kind of rolling around there. I hate these. I get stuck with these more than any others, including the big metal tops, the big metal top pins. But the problem is, can you mount this candle on a wall in such a way that it could burn to its conclusion, that is all the way down, burn the entire wick without singeing the wall? And what that means, obviously, is we can't light the candle and use the wax to stick the base of the candle to the wall sideways. You're going to have to put it up somehow straight. Have you seen Dunker's candle problem before? Anybody know the solution? Well, that's one that might throw you for a while, because one of the things we've played on there is what's called functional fixedness. That is, the actual solution to this problem is pretty straightforward. Unfortunately, I don't have a bulletin board, or I would have put, you guys should feel happy, because otherwise I would have put one of you up there and come back to you for 5 or 10 minutes and watch you struggle with it. But in essence, the box is there deliberately holding the tacks. But in fact, the box is what you need in order to solve the problem. That is, what you have to do basically is to take the box, empty it of the tacks, and then, assuming this were a bulletin board instead of the side of a monitor that I'm looking at, what you would do is to take the box and tack it, or you could put it this way if you had tape. What you're going to do is to tack it onto the monitor this way, or tack it onto the bulletin board this way. Now you have a platform for yourself, and onto that you then put a little bit of wax and mount the candle, so that this is the solution that you end up with. Okay? Candle attached to box, attached to monitor. But in that case, what has happened is that it's the way the problem is deliberately presented is that you put the tacks in a box, plainly labeled tacks or something like that. And in fact, what that gets people thinking of is they're not paying attention to the box. They're thinking constantly about, you know, gosh, can I break the candle and stick it out sideways from the monitor? Well, no, because then you can't burn the entire wick. So in essence, in that case, what we've done is to play on your functional fixedness relative to the tacks, because we've put them in the box that they normally come in, and you tend to think of the box only as container rather than as platform holder in that kind of situation. So in essence, what we're dealing with there is a classic in problem-solving literature, and that is what's called the candle problem of Duncker. It was originally proposed back in 1945. And there's another one. Unfortunately, I was not able to get this one set up at all, but another devious way to do the candle problem is to throw in something extra, like I started to bring with me a roll of tape, although that might have been a potential help relative to the thumbtacks. Tape would have been better, given that I was working on the side of a monitor there, or throw in a piece of string, which is actually totally a distractor. The string doesn't help you at all in that particular situation, unless you need to re-wick the candle or something like that. But the problem is to get to the essence of the problem in trying to solve it. And one that I was not able to set up, unfortunately, is the next one that I've listed here, which is a classic also called the string problem. If you can imagine this for a minute, our ceiling here is 2-foot tiles with strips down it. And what I should have been able to do, we just did not have time, and I don't have string, but tie a string that hangs down maybe 2 feet off the floor, such that, well, let me describe the problem first. You have another string strung further over, also hanging down about 2 feet off the floor, adjusted some distance apart so that you cannot grab one string and pull it over to its extent, you know, get a diagonal between your hand and the string where it's attached to the ceiling, and you can't reach the other string. And the challenge is, can you get those two strings tied together? That is, they're far enough apart so they're hanging and you can't grab one and pull and get to the other. But the solution to that one is a little tricky, and what you sometimes do, well, one way to cue the correct answer is to have the researcher walk past and with his shoulder or something hit the string so that it starts moving ever so slowly. Because the actual solution is that there is within reach something heavy, like the microphone box, the broadcast unit of the microphone that I'm talking off of, or something like that, or scissors or a wrench or something like that around. And the trick is that what you have to do is to tie the wrench or whatever you've got, some heavy object, to make a pendulum out of one of the strings and then set it swinging. Okay, and get a pretty good arc on that swing. Then you can very casually walk over, grab the other string, pull it towards you, and then when the scissors arrive, catch it, and then connect the two. But the solution there is you've got a string so many feet away from another one hanging from the ceiling that there's no way you can grab one and pull it and have enough arm reach left to get to that other string. So in essence, in both cases there, what we're playing on is to kind of break set. Think about new creative ways in which to solve that problem. And the thing that we're going to come back and talk about later that really plays a role in both of these problems is functional fixedness. Because if I might have, in fact, if I were going to set this up in the class, I'd worried about trying to get it set up before I started the tape. And I finally realized that what I was going to bring was a big pair of silver scissors, and I couldn't find string when I needed it. But I was going to bring a big pair of silver scissors and very deliberately use them to cut the string. But I was going to tie it over the thing, the strips that these plastic tiles fit into, and then use the scissors to very deliberately cut them, and then put them on the desk, and then walk over to the other string, hang it again, use the scissors very deliberately to cut them, so that twice I had demonstrated the purpose of scissors in that particular situation. And what that tends to do, if you're not able to spring out of thinking only about scissors as scissors, only about a box as a container, not as a shelf, then you tend to exhibit what is called functional fixedness. We'll have a whole unit here in the next tape on functional fixedness and some of the disruptions that it can cause for us in problem solving. But let me give you another one here that we are fully prepared to demonstrate for you, and that is what's called the alter window problem. This was developed by Mike Wertheimer back in the night. I think it was the 50s. I forgot to check the reference on this one. But in essence, it's a very tricky kind of problem, because in this case, what you're going to do is the following. You are given a window, okay? The window is round. It is to be decorated by surrounding it with gold leaf paint. And what the artist has decided on is a diagram that I will build for you in a minute. But the area that is to be decorated is bounded by two lines, two parallel vertical lines that are tangential to the edge. They are tangent to the edge of the circle, as you can see on the diagram there. Okay, so the two circles just barely touch. I'm sorry, the two vertical lines just barely touch the vertical part of the circles there. So the lines are tangential to the circle. They're the same length as the diameter of the circle. That is, if I were to move either one of those lines over to the left or right, it would exactly equal the diameter of the circle. And these circles are joined by semicircles at the top and at the bottom. Okay, so the overall figure that you have is two semicircles separated by two lines that are the width or the length of the diameter of the circle. And in essence, the area that is to be painted is gold. This is as close as I could get to gold with PowerPoint, so I'm a little disappointed in that, but let's pretend like it's fading gold. What's the area that is to be painted? What is the area that is to be painted in gold leaf, if that's the design that the artist has come up with? And you saw me construct it, so you know all of the elements that are involved there. Any ideas? How do you go about solving that? I can give you some hints. Whoops, I went the wrong way here. I guess I'm not prepared to do that yet. Let me go back to that and pose it for you for a minute. I thought I had some hints. I guess that's on a later problem that I'm going to give you some hints. But we know, for instance, the diameter of the circle. We can calculate the area of the circle. Pi d, what is it? Pi r squared. Okay, so we can calculate the area of the circle. We could calculate the area of the square. But how do you end up solving it? We could calculate the area of the circle. We could calculate the area of the semicircle. But how about the area of the four funny-shaped remainders? How do you handle that? Well, if you think about it in terms of the way you saw me and consult with somebody who has no math training, it may occur to them, which is the actual key to solving this problem, that those four funny-shaped areas actually complete a square, if you think about it. Okay, so that the total area to be painted is actually exactly a square the size of the diameter of the original window, if you think about it. The semicircles, I told you that the two vertical lines were tangential to the circle. The vertical lines were tangential, so that means they are projecting upward something that is exactly the diameter of the circle. So the semicircle that joins it simply includes half of the same area as the circle, which is the window itself. And so basically, if you move those mentally, if you just take those two semicircles of gold and move them back into the center of the, or use them to cover the circle, what you end up with is a square of paint, which is exactly the same size as the on edge as the diameter of the circle itself. So in fact, you don't need any particular math to solve that. When I first saw that, I was busy working about, well, let's see, okay, we can calculate the circle, we can calculate the square, and then we subtract the circle, and then we add that back in, and of course you've solved the problem, because you don't have to subtract it to add it back in. You just leave it there and calculate the area of the square, and the problem is done. Wertheimer looked at how people solved this, and what he discovered was two different kinds of problems, or a particular problem that tended to occur, and that was that what people tended to become was structurally blind. What they tend to do is to reproduce thinking used in other situations when it's inappropriate to the newer situation. That is, although you and I are well trained in geometry to calculate areas of squares and circles and all manner of different things, it isn't necessary in this case. All you have to do is step outside the box and look logically at what you're being asked to paint in that, or the area that you're being asked to calculate in that particular situation. And so basically, the obverse of being structurally blind is to demonstrate instead what is called productive thinking. Productive thinking essentially involves showing sensitivity to the structural requirements of the existing problem in that situation. And so in that case, as I've verbally described for you, it was possible to, having a grasp of the general principle of squares and circles, and then applying it to the particular problem that was posed for us there. Which leads us then directly into a discussion of insight problems. And insight problems come in a marvelous array of possible combinations, okay? I'm going to define insight for you essentially as the sudden discovery of a solution following a period of unsuccessful attempts to solve a problem. Now, therein lies an interesting bit of argument between Gestalt psychologists and behaviorists. If you've read in the history of psychology, there was a very interesting exchange between behaviorists and Gestalt psychologists. One in particular involved a Gestalt psychologist who was, I believe it was Kafka, but I'm not absolutely positive, who was on an island during the First World War. And had a bunch of monkeys with him, which he ended up deciding to study. Being a scientist and being isolated because of the travesties of the war, he started studying the monkeys. And what he found was that if they were put in a situation, one of the classic ones involved having a monkey in a cage where a banana is hanging from the ceiling, and the monkey, jump as he could not get high enough to grab the banana. But there were 3 different cardboard boxes or wooden boxes in the cage, and so eventually the monkey was moving the boxes around, and as it is described by the Gestaltists, they talked about sudden insight enlightening his face or his activities. And what he did then was simply take the box, stack it on top of one of the other boxes, move the original one under the string where the banana was, move a second one in and lift it on top, and then move a third one in and put it on top, staggered in such a way that the monkey could then very calmly walk up the boxes and grab the string. The behaviorists didn't like the idea that sudden insight occurred. And in essence, what they were ultimately able to demonstrate was the development of problem-solving skill. They took chimps in a whole series of studies, but they did a different kind of study in which what they did was to have a problem that could be very easily solved in 1 of 2 or 3 different ways. And so in essence, you had 6 trials with a given problem. And the odds were 50-50 that they would solve it the first time. Gradually, in the first few trials, they struggled. I mean, the monkeys could not solve the particular problem. But by the time they had solved 300 of similar problems, where depending on the order in which you did things, information was revealed to you that would allow you to solve the problem. What they found was that within 300 trials, what had happened was problem number 1 was at chance level. That is, when you had your first shot at solving the problem, it was purely chance. It was 50-50 whether you would in fact make the correct move to solve the problem. But once you made that move, if you did it astutely, alert to the things that were involved, you got all the information you needed in order to be able to solve the problem. And so the problem-solving curve, then, behavior curve, went from 50% on trial 1 to essentially 100% on the remaining curves. And in essence, what the article was essentially saying, insight, ? And what they were really talking about was the accumulated skills of learning to solve problems. It was essentially a learning-to-learn case. And when you had a monkey that had been in a cage for years, during the First World War, solving those kind of problems, the given was, and what the monkey came to know was, there is a solution. And he has put in here what I need to do that with. And so, when they show insights, in quote, what the behaviors were arguing was no, they were just showing the cumulative effects of learning to learn, learning how to solve that particular problem. So there is, when we talk about insight, we do qualify it as essentially the sudden discovery of a solution following a period of unsuccessful attempts. But you'll find that if you're posed the same kind of problem over time, insight happens very rapidly. So I don't want to unduly enamor insight of too much importance in this particular situation. Let's give you one. This is an insight problem. We have a pin pattern here, 9, 3, 6, 10 pins. I want you to move only 3 pins and invert that triangle. That is, we've got a very clear triangle represented here, okay? What I want you to do is to move not more than 3 pins and convert that into a triangle which is standing on its nose, okay? Any idea on what to do? That's a thinker. Let me give you a hint. So the problem here is to move not more than 3 pins and get a triangle which is standing on its nose instead of on its base, as this one is. I'll give you a second hint. What's depicted there obviously are directions to move particular pins. Anybody got it? So what do you do?
You move the bottom right down?
Yes. And so basically by doing all 3 of those, the net effect is that you get this. Okay, the 2, 3, 5, 7 pins in the middle don't move, but the 3 on the corners are simply now moved, each clockwise or counterclockwise. Or you can move it directly across, I don't care. But the net effect is, once you solve the first one, the other 2 follow pretty easily, and certainly by the time you've got 2 worked out, learning to be able to do that is quite a bit easier. So the goal in that case is to create an inverted triangle from the stable triangle that we started with. And the key is learning to move the corner pins. So what we're dealing with there is insight problems. Let me give you another example of a somewhat more complex one. In this case, we have, this is where I was going to give you the hints. We've got rings, okay? These are materials in which, again, I've used gold here. We've used materials to create rings, and we want you to build a bracelet. But there's a limit. In order to build the bracelet, you have to break some of the rings, okay? If you, in fact, close a link, it's 3 cents. Whoops, it didn't come out in the correct order here. That's what I get for not double checking. If you break a link, if you have to open a link up, it costs you 2 cents. Okay? If you have to resolder it to close it, it costs you 3 cents. So breaking a link so as to link link it to another link costs you 2 cents. To solder it back together to make it a whole link again so it'll hold the chain, it takes 3 cents. Can you build a bracelet for not more than 15 cents? In other words, not more than 3 breaks. Can you do it? And again, the solution, when it occurs to you, will come pretty rapidly in all likelihood. You will demonstrate insight. Anyone? I'm going to spend 6 cents right here, okay? I'm going to take those 3 links and I'm going to break them. I've already invested 6 cents. So I've got 9 to pull it all back together again with. Can I do it? Yeah, I'm going to take those middle links and move them out that way. And then I'm going to put the chain links in that way. So soldering those 3 back together is going to be 9 more cents, and I've built a bracelet for 15 cents. All you have to do is take, because the other tendency, since you had 4 links, was to take each and break one and hook it to the next one, and then break another one and hook it to the next one. But the trick is you've got to get one of those to serve double duty. So when you join it all back together, you get 2 hooks for 1, 2 for the price of 1 in that situation. That's the realization that you have to come to. And given that it is at least hinted, my bet would be that if I had shown those as 2 links, or links of 2 and a single, or actually 6 pairs of 2 links, it probably would have taken even longer to, well, financially it couldn't have been done that way. But if the pieces had been had been presented other than the way they were with rows of 3, it might have taken even longer to do that. That is, how that problem is presented to a certain extent hints at what is required, because you're organized to think in terms of 3 when you start with 4 rows of 3 links, and something is kind of implicitly involved in breaking the 3 links in order to solve that particular problem. Now I'll give you the most complex of the insight problems that I wanted to share with you here. Okay? Suppose that we know that A in this particular puzzle is 6 inches. Okay? We know that as a fact. We also know that B is 6.5 inches. Those are the starting premises. A is 6 inches, B is 6.5 inches, given. The goal is to find the area of the square plus the strip. Find the area of the square, and by square what I mean essentially is, and that's of course the formula for finding a square, a squared equals 36 inches. What that's labeling is this particular feature. So what you really have to figure out then is there a way to do it easier than figuring out that you have to take 2 triangles 6 by 6 and solve it twice and add that to the overall square width of the 36-inch square. Is there a simpler way to do that? So let's remove the square so it doesn't hinder you. But you need to find the area of the square plus the strip in the simplest possible way. And this one, I was amazed. I did figure this one out, but it takes a while. And there's a very simple solution.
Don't you just have 2 triangles?
Bingo. Yes, exactly. What it has is 2 triangles if you look at it. And so what we do, just to show you, I'm going to take I think it's the upper one that moves. I'm going to just move the upper one and show you what's happening. Okay? So when you move it up just a little bit, now what you've actually got is a square that is A by B. And so in essence, all you need to do is square 6.5 to solve that particular problem, depending on how you technically want to describe it. But the square plus the strips is actually solved by simply moving that back, moving it up so that it becomes the square that it truly is from which it was originally made. So that's the starting problem. There's the solution, essentially. You don't even have to do it more than, you don't even have to go through the triangle formula. All you have to do is multiply A times B to solve the problem in that situation. Okay? What is required here is insight into the structure of the problem. That is, you have to be able to look at the independent components there and realize all of a sudden that they're on the same the same horizontal dimension. They are both the same width. And in fact, if you move one of the triangles up or the other one down, it very quickly lines up as simply a square split diagonally into, a rectangle split diagonally into 2 triangles. Structurally blind thinking may generate an answer, even a correct one. That is, I suggested one of calculating the square and then adding the triangles to it. But without a correct understanding of it, such blind solutions usually do not generalize well to other problems. And so the difficulty with the insight problems is that if you solve it blindly, and that may happen, you may stumble on the correct answer, but if you can't justify how you got it, it's unlikely to benefit you the next time you have to solve such a problem. Let me give you a number and ask, using a sample of I'm going to give you a couple of number insight problems as another type of insight difficulty or posings. If I give you this number, 1 plus 3 zeros plus 3 zeros plus 2 zeros, 8. In other words, 1,000,000,008. Can you tell me quickly whether that number can be divided by 9? And there's a math rule, a trick that you have to know in order to solve this particular problem. One way, easily enough, is to subtract 9 from it And then you end up with 999,999,999, which obviously is divisible by 9. And since you took 9 away, the answer is yes. But the other way is that you add, and I thought I had the solution on here. I guess I don't. So let me just go back to it for a second. The solution is simply add up the numbers of any given number. And if it totals to 9, or a number that's divisible by 9, then that number itself is divisible by 9. Okay? So we could even make it, well, you could make it 1,098,000,098. And since we've now got 18 total, 1 plus 9 plus 8, it is divisible by 9. The same is true of any number divisible by 3. If the numbers add to a number which itself is divisible by 3, then by definition that number itself is divisible by 3. So in that case, the insight that you have to come to is to understand something about the relations to numbers. But they do often, insightful solutions do often generalize to other solutions or situations, because if you realize the 9 works, then by implication clearly the 3 would have to work, and so forth. Gestaltists are interested in other types of problems in addition to these numerical insight problems. For instance, suppose you want to go to a church meeting on campus, but you're forgetful. You want to run for president at this club meeting I said church meeting, what I meant to say was club meeting. You want to go to a club meeting on campus, but you're forgetful. You want to run for president of that club at the next meeting since elections are being held. You ask a friend to remind you when the club meets, to remind you that it is in fact meeting on a particular day. You learn eventually that the club has met. Why didn't your good friend call you? Okay, and you later get an announcement. Your friend has been nominated for president of that club. Okay? And so in that situation, you have an immediate revision of the status of good friend based on the general principle that good friends honor good friends' requests, and good friends are honest reciprocals. That is, they reciprocate, they deal with each other honestly. Good friends treat each other with honesty, with honor in all cases. Can you think of anyone nationally, the opinion of whom has been massively revised? I can think of a couple of different examples. There was an advertising legend for Hertz cars by the name of O.J. Simpson, whose reputation took a real nosedive based on accumulated evidence. Not the conviction, but the accumulated evidence. That's a case where evidence will sometimes take hard-won and hard-fought opinions about people and result in significant kinds of changes, because in that case what you gained is a certain kind of insight of the person based on how they behaved. So insight isn't necessarily limited only to mechanical problems, is the point that I'm essentially making here. And then let's look at some others where you have to actually induce structure, and you can help me solve one where I can't figure out what the correct answer is. I've got the answer, I don't know how I got it. Okay? So if we're inducing structure, in the previous case, the structure is flexible. That is, you can work with it and try different kinds of combinations. Here, it's rigid. The task is to discover what the structure is. And so now what we're dealing with is, for instance, problems that involve series completions. These run you nuts, run me buggy, okay? For instance, if you are given 1, 2, 3, 5, 8, and 13, what is the next number in the series? And how did you generate it?
1 plus 2 is 3, 3 plus 2 is 5.
Okay, so the rule then that is used there is add the last 2 to get the next one. 1 plus 2 is 3, plus 2 is 5, plus 3 is 8, plus 5 is plus 8 is plus 5 is 13, plus 8 is 21, and so forth. So the next one would be 35, 34, and so forth. Okay? Okay, you're doing well. How about 1, 2, 4, 3, 4, 6, 5, 6, and then what? Nope, not 7. 8's the correct answer. How did you get it? Yeah. Forward 1, minus 1. Sorry, that's not correct. Add 1, add 2. Take away 1. Sorry, the middle number should be plus on the screen here. That should be plus 2. So it's plus 1 plus 2 minus 1. Okay? The one I can't solve is this one. I can tell you what the correct answer is, but I don't know how to get it. If anybody can bail me out on that one, I would be deeply appreciative. Well, I'll just leave you to sweat on that one then. But in that case, there is a specific answer which is available to us, and the fun in it is that the rigidity is unalterable. Okay? We'll leave you to ponder that one. If anybody gets it to me for an A in the course, let me know. I tease. Analogy problems. Let's try the following. Barn is to house as stall is to. Unfortunately, the answer is published in the current version of the book. That will be corrected in the 3rd edition, so that you'll have to puzzle this one. I found this in a quick and dirty intelligence test a number of years ago, and it is a very clever item if you think about it for a while, because a lot of people try to make it kitchen or bathroom or living room. But in fact, it's the concept itself, the generic, is what's really being referred to there, because in a barn, a stall is the room. It is the kitchen, it's the dining room, it's the bathroom, it's the bedroom, it's everything as one. So the actual correct answer there is barn is to house as stall is to room. R-O-O-M. And what we're using here, of course, is an analogy. You have or will stumble into analogies in a couple of very interesting ways. For instance, it's used a great deal in tests of intelligence, and you're going to see it when you apply, if you apply to graduate school. One of the bears that you will tackle is something called the Miller Analogies test, which is only about 45 or 50 increasingly difficult problems. And by increasingly difficult, what I mean is that they start with obtuse ones and go down from there. So it is a real brain tease to solve the analogies in the Miller Analogies test, which is nothing but analogies, one-page answer sheet. And another one is the graduate record exam, which also tends to use analogies in some of its exam questions, as for instance does the SAT, the Scholastic aptitude or achievement abilities test, I guess is what they now call it. All of them use analogies in one way or another. And the example that I gave you there, barn is to house as stall is to, correct answer, room, involves basically finding relationships among the parts that are involved there and then trying to fit the relationships into a pattern. That's basically what you have to do. Figure out what the relation is between 1 and 2, and then find out what the implication is for the relationship between 3 and 4. Or it may be a relationship between 1 and 3, which implies the relationship between 2 and 4, the second and fourth term. Robert Sternberg in 1977 developed a model of the process that he believes is applied in solving this kind of a situation. And so the given in that case is the 4-word puzzle, and it can take any of a number of different possibilities. But in essence, the solution then is to find the relations, fit the relations into a pattern. That's basically what you have to do. And what Sternberg originally proposed back in 1977 was something that Sternberg and Gardner actually worked on quite a bit in the ensuing years. But another kind of problem like this is given Washington is to Lincoln as 1 is to blank. What's the answer? Washington is to Lincoln as 1 is to blank. The solution is either 5 or 10. And in essence, do you understand the basis on which that's done? Because that's a little subtle, the leap that's made there. Why is 5 the correct answer? Yeah. Washington is on the $1 bill. Lincoln is on the $5 bill. What I meant to check was coinage. Do I remember that Washington is on one of the coins and is Lincoln on one? Is the penny the one that has Washington? Has Lincoln. And which one has Washington? The quarter. Okay. That won't work. Yes?
Couldn't you say it was by their rank in the order of precedence?
Yeah.
That would make 16 another potentially correct answer. That's good. That would fit in that situation. I instantly leapt to money, I guess, but but yeah, certainly order of presidency would also work. Okay, so I'll add another option there as a possible solution. But in essence now what Sternberg did was to look at the kind of thing that you and I were just talking about here in terms of a basis for solving the problem. And what he suggested is that there are really 4 elements that are involved in his work originally in 1977. And that is, first of all, what you have to do is to, and it was followed up, as I said, by Sternberg and Gardner in the early 80s. What he says is that the very first thing that we have to do is to encode the problem. That is, what you have to do is to identify the important, relevant characteristics of the problem. What is the particular features that's relevant in this situation? You may do that by just free associating, kind of think of things that apply to each of the first 2 terms. So we could think of the fact that Washington was first president, he was a general, he was also on the dollar bill. We could argue that Lincoln was president, which provides the basis for one of the 2 suggested solutions. He was a war hero to most, and he was on the $5 bill. Okay? And so Lincoln can be, you can do a kind of a free association, and in essence what you're doing there is encoding some of the potential bases for solving the problem in doing that kind of free association with what does that concept make me think of, and what does this concept make me think of. Second situation then that we have to engage in, according to Sternberg, I should say, is inference. That is, we have to infer, we have to establish a valid relationship between the first 2 items. How does the A item relate to the B item is an obvious feature in solving this, because until we know the relationship between A and B, we can't possibly work out the relationship between C and D, or the number 3 and the number 4 item. And then what you have to do is what Sternberg calls mapping. Okay? But in essence, inference is involved in establishing valid relationships between the first 2 terms as the situation in inference. Thirdly then, we have to engage in mapping. I may have skipped one in my talking there a minute ago, but in essence, encoding, then inference, then mapping. And what we're doing there is to establish valid relationships between the first and the third term. That is, in what we're getting into solving the second half of the puzzle there. How do we map what we've learned and inferred from the relationships among the first 2, and how does it carry over then to what's the relationship of number 3 to number 1 in that situation? And so we're mapping on the information from the first 2 in terms of how it could feasibly interact with the number 3 item. And finally then, what you do is to, okay, so again, I forgot to add the explanations here. You establish valid relationships between the first and the third term when you're mapping. And what you're mapping here is the information you've generated here and the inferences you've made in the relation between 1 and 2. So we free associate to 1 and 2, we draw links between 1 and 2, and then we map that onto what does that say about possible positions for number 3 in the 1, 2, 3 ordering. And so the third thing is to establish valid relationships between the first and the third terms. And finally then, we apply the information that we've generated. And there are a couple of different ways in which we can do this. First of all, what we can do is to use the information that we've generated in this situation to establish valid relationships between between the second and possible 4th terms. That is, whatever our possibilities are for answers, what we're looking for is the best possible answer. And in this situation, relative to Washington and Lincoln and the number 1, we generated 2 perfectly defensible answers in that situation. So the application involves establishing relationships between Lincoln and the possible 4th term. That is, now what you're trying to do is to link up 2 and 4. In that situation, so that 1 is to 3 equals 2 is to 4, or is similar. And in fact, this latter essentially, in terms of application, builds on the inferencing and the inferences and the mapping that you have already done in this situation. So it becomes essentially a cumulative process. The first, second, and third steps are clearly related to the terms themselves, but you build from that into the application, where you actually solve the problem in that particular situation. Sternberg and Gardner in 1983 in a subsequent publication. Let me back off, comment there on the fact that those two as authors is a unique but predictable combination. Do you know what the link is between them? Where do the names Sternberg and Gardner both appear? In what area? Testing of intelligence. Both of them are involved in the testing of intelligence. Both of them produced significant books in the study of intelligence, because intelligence had fallen on pretty flat times in the 1940s and the 50s, and it was the books by both of them in the 60s, 70s even, the 80s in fact, I'll get it straight eventually, in the 80s, that really put the testing of intelligence, reinvigorated it essentially, because Sternberg was arguing that we have the traditional tests basically look at knowledge, accumulated knowledge. That would be the Stanford-Binet. The Wechsler looks at essentially application of principles, so operating rules. But nobody has looked at argued Sternberg, nobody has looked at the issues of when you make a decision. If you're in a math problem trying to solve it, and you realize partway through your algebra test this is going nowhere, and you end up with great crocodile tears tearing up your answer sheet and starting again. Sternberg is arguing that doesn't come out of either knowledge or the operating rules. It comes instead out of a metacognitive process where you're thinking about thinking. And that was Sternberg's contribution. Gardner's contribution was the idea of he created a theory of intelligence that basically argued that there are more ways to excel than just in terms of number skill and word skill and the various academic skills. He ended up creating a theory which at the current time is based on 8 independent types of intelligence: intrapersonal, interpersonal, one of which involves athleticism. There's no other theory of intelligence that has ever given credit to stellar athletes and the fact that they are extraordinarily gifted at what they do and can certainly earn a very adequate livelihood. So I'm off topic, I come back. Sternberg and Gardner is a very powerful combination of people that have a lot to say about creative thinking and problem solving and so forth. And basically they demonstrated in their work that there are really significant correlations that exist in student abilities to handle inference and mapping and application on all 3 types. That is, if students are good in one, what they tend to be good at is the other 2. That is, the one tends to predict well how well they'll be able to do the other 2. So in general, you have a kind of a rising generic ability in terms of problem solving or matching problems as we're into right now. And in essence, what's really involved there is the structure that we were talking about, and that is that the application really involves inducing structure in the 4-element A is to B is C is to question mark. And so there are really 3 different things that are involved there. One is being able to complete the task. The second is skills with analogy itself. And the third is the skills involved in classification. Students that are good at doing any one of the types of tasks were also good at the other 2. That is, if they were good at completing them, they tended to be good at creating or understanding analogies, and also at classifying the relevant information so it could be organized or reorganized is the correct word in order to solve the problem. The bottom line conclusion here, tying back to Greeno, whom I mentioned at the beginning of this entire series of comments, is that there do seem to be some common skills. That is, that when you find the one, you tend to find the others in terms of things like ability to solve analogs. Now let's look at a different kind of problem. Now let's look instead at what are called transformation problems. These are problems that have a structure that you will be familiar with it as soon as I point it out to you. But basically they have 3 states when they're posed to us. They have basically, first of all, an initial state. This is the current situation, okay? And then they have a final or goal state, which is provided. That is, you're told, here's where we are, here's where we want to be. And then what they do is to put a certain kind of set of limiters on you. There is a sequence of operations that is implied, but getting from the initial state to the goal state is going to involve a sequence of operations because of the kind of rules that are applied in the situation that is described. There are a number of different examples that I could use here, but in essence, the particular one that I'm going to choose is the missionary and cannibals problem. The situation is that 3 missionaries and 3 cannibals have reached a river. They are trying to cross the river, and the goal is, can they get across there with the following proviso? They have a boat that will carry only 2 people at any given time. It'll carry 2 people and no more. It is the case, as we know, in relations between cannibals and anybody else. I started to say canaries. Between cannibals and anybody else is cannibals tend to eat people, particularly if they're in the majority. So the obvious rule in this situation in cannibals and ministers, or whatever is the group we're traveling with, missionaries, is that at no time can there be other than an equal number. And if there is an unequal number, it has to be the case that the missionaries have the greater number. Okay? So you have 3 and 3. What's the first thing you do? Solving the problem. You've got a canoe that'll carry 2 people. You guys are going to spend a lot of time on the riverside. You have a canoe. You could send 1 missionary. You could send 1 cannibal. You could send 1 of each, or you could send 2 of either one. So what do you do? 1 of each, yes. So a canary and a cannibal go across. Who comes back? Remember the rule, there can't be a majority of cannibals anytime. So the missionary has to come back. Now we've got 3 missionaries, 2 cannibals. Now what do we do? We've got 3 missionaries, 2 cannibals. We've got a missionary over there. So there has to be at least 1 missionary in the canoe that goes back over. And if it's 1 and 1, a missionary and a cannibal, when you get to the far side, that missionary is going to be devoured because you then got 2 cannibals and 1 missionary. So we can't send.
Did you say if it's also equal?
If it's equal, it's okay. So we've got 1 cannibal on one side and 2 cannibals and 3 missionaries on the other side. Who goes over next?
And 1 cannibal. Oh, without the missionary. So there would be 2 cannibals on one side.
But then you got to have somebody get the canoe back.
2 missionaries.
2 missionaries. You need to be on the mic so that people can enjoy what's going on here. But somebody suggested sending 1 more missionary, 1 more cannibal over, which is good, except somebody's got to bring, so we're back where we started. So you send 2, what are you saying? 2 missionaries over? But now you've got 2 cannibals and 1 missionary left on shore on the starting side. So actually what you have to do is to send both cannibals over. Now we've got 3 cannibals on one side, 3 missionaries on the other. We have the 1 cannibal bring the canoe back. Okay? So now we've got 3 missionaries, 1 cannibal. Everybody's safe. Cannibals are still hungry. And now what do you send across? 2 missionaries, because that leaves 1 and 1 on the starting side and ends up with 2 joining 2 on the other side. So now we've got 2/3 of it solved. What do we send back? This is where it gets tricky. So now we've got, I've lost track. We have 1 of each on the other side. And we've got 2 and 2. We sent the 2 missionaries over. So now we've got 3 missionaries, 1 cannibal. We send the cannibal back, who brings over a cannibal. We send the cannibal back again to bring over the other cannibal. Problem is solved. Okay? So that in essence, in that case, what you're really trying to engage in, and the most efficient way to really solve that problem, is to engage in what is called a means-end analysis. That is, we want to look at, we know the end state. We want 6 people on the far side. We know the beginning state. We've got 6 people on the near side. Those are the end points. A means-end analysis is simply, given the rules, whatever they may be, and in this problem it is simply no majority of cannibals at any time in the exchange. How do we work it out? And so you do a means-end analysis. So just like we did, we started with 6 people on one side. In order to preserve the balance, the only thing we could do was to send one of each over. Or we could send 2 cannibals over. Those were the only 2 limiting conditions that could be used in that situation. Okay? And so the end impacts the mean given the operating rules in that particular situation. Okay? So having only one canoe that'll carry 2 people, it forces you to think creatively about doing such activities. Basically, solving such problems requires the use of that means-end analysis, and the solution can be constantly checked for adequacy against the goal. That is, you can solve that problem step by step, and as we did, you're simply going through it, looking at the nature of the problem itself in terms of how you're actually going to solve it. And so the means-end analysis then is diagrammed simply as, or is defined simply as, a plan of operation that is used to solve transformation problems by eliminating differences between an initial state, which has been specified, of a problem, and the specified or goal state. So we give you the start and the finish and the limiting rules in terms of how it is to actually be conducted. And in fact, that is the solution that we end up with in that particular situation. Let me give you another one, which is related to this, but different in a particular way. And that is, if you will take out 3 coins of different size on your desktop there, I want to work another problem with you, which is also of this type. It is a transformation problem with one difference. Okay, take out 3 coins. I'm using a quarter, a nickel, and a penny. And I want you to stack them in that order. You can use a quarter, a penny, and any 3 out of those 4 will have the size difference that is required in this situation. Stack your 3 coins, largest on bottom, smallest on top. And what we're going to do here is the following. The beginning state in this situation is bottom coin, largest coin on the bottom, middle coin in the middle, and smallest coin on the top. The end state is that you are to move all 3 of those coins to another stack, 2 positions over. So you've got this stack in point A, you've got a point B where you can stop, but you're to end up with all 3 coins stacked, largest on the bottom, middle in the middle, and smallest on the top, 2 positions over. So you could think of it as being like on a checkerboard if you want. You can go from one square to the next, and it's the 3rd square where you have to have them all stacked up as smallest, middle, and largest. Sorry, the other way around, largest, middle, and smallest. And the limiting rule, like in the cannibal missionaries problem, at no time could the cannibals outnumber the missionaries. In this case, the limiting rule is at no time is a larger coin to be on top of a smaller coin. Okay? So the question is, can you move those coins from the small, middle, large stack to an identical small, middle, large stack 2 positions over? And so in this case, the only coin you can move initially is the smallest one. You can move it 1 position over, but if you do that, you're then going to have another coin land on top of it. So the obvious thing to do is to move that coin 2 positions over. Okay, so you move the dime or the penny, whichever is your smallest coin, 2 positions over. Now we've got middle and large stacked that way in the left position. Now what we do is what? What limits do we have? What can we do here? We can either move the penny, which we just did, or the nickel. And obviously the nickel is the next thing to move. Where can it go? It can only go in the middle position. Okay? So now what we've got is the big quarter on the left, the nickel in the middle, the penny on the right. I'm moving left to right. If you're left-handed, you're going the other way. What can we do now? We've got one coin in each slot.
Put the penny on the nickel?
Yeah, the only possibility then is to put the penny on the nickel. And in fact, what we're then going to do is what? So now we've got the quarter on one side, the nickel on the bottom, the penny in the middle. Everything's legal. We still don't have anything in the right-hand position, which is our goal. Except the other coins are already in the middle position. So what we actually are going to do then is probably move the penny back over so that it's on top of the quarter. Still got the same smallest, no bigger coin is on top. Now we move the nickel over. Okay? Now we're going to move the penny to the middle, and in fact we're going to put that over on top of the nickel. We now have penny and nickel over. Theoretically, we've already done enough moves to understand the rule because we have now moved two coins in the proper order over to the right side. So if you're keeping track of the moves, you've actually already generated all the math you need to in terms of what's to be done. But to solve the rest of this problem, we're then going to move the quarter to the middle. We're then going to move the penny from the right-hand side to the middle and then over to the left. The only thing that can then move is either the nickel or the penny, because the only landing spot is in the middle, because the quarter can't move either direction because it would be bigger. So we'll move the nickel back to the center position. That isn't going to work. Yes, it will. The penny to the middle. I'm not going to finish this in 22 seconds. Penny goes to the right. Nickel goes to the left. Penny comes back. Penny goes over to the left. Quarter moves over. Penny's on top. Penny goes to the middle. Penny comes over. Nickel goes to the middle. Penny comes back. Penny goes over. Nickel goes. Penny's there. We finished it.